So as you probably saw my announcement, I did something really stupid over the weekend. I mean, last night. Speaking of weekend. Last night, I thought, the section on principal component analysis is coming up in the book. Principal component analysis is extremely important in applications in a lot of different areas. And oh, by the way, I have 2 published papers on the subject. So I thought we should talk about PCA. It's a really great, important application. So I decided to skip the next section. And the next section was on linear regression, which is, of course, a very important and interesting application. So I'm trading one application for another. So it seems kind of pointless. But I've already committed to it, and there's no turning back now. So, I sort of set myself up for a kind of nearly impossible task of covering 3 sections of material in the next 2 days. Also, this material is not going to be on the final exam, so now you feel really motivated. Okay, anyway, linear regression, just really quickly, you're taking, let's say, in the most simplified example, we got something in data points in 2 dimensions. Something like that, okay? Those are dots. Imagine they're dots. And you want to fit a model to them, and your model says that there's basically a linear relationship between whatever variable you are plotting on the x-axis and whatever variable you're plotting on the y-axis. It's something like, not a linear relationship, but a relationship that fits a line. So linear in that sense. So we might think it has the equation y equals mx plus b. And we want to, and then it's y equals mx plus b, and then plus some kind of, I don't know what terminology statisticians use for these things, so I'm just going to use dot, dot, dot to signify some other stuff. But the other stuff is basically noise. So there's some random amount that it deviates from the model. And there's sort of like this idea that there's an underlying relationship, and then there's a little bit of noise that gets added in because we live in the real world, and so all measurements are noisy. And the goal is to find a line that best fits this data. So it sort of minimizes the difference between this linear model that we have and this noise. We're trying to find the line that best fits the data. And so that's what linear regression does. We take our data, so we might call it a big matrix X, and our data points are xi and yi. So we might do something like x1, 1, x2, 1, xn, 1. And, well, what is the purpose of the 1? It's so that we can fit this with a, maybe I did this wrong. Did I do this wrong? Yeah, the data points should be 1. There we go. What we're trying to, this is x. Well, let's just, I'm going to write a big X above it to call it x. I want to multiply this by mb. And this is equal to y1, y2, yn. So what we're saying is that everything over here should be represented as a linear combination of the x, and then this 1 just allows us to add or subtract some constant. So that's where that 1 comes from. And when we solve this, well, this is clearly an over-constrained system because it's got 2 columns and a bunch of rows. So this is not going to have a solution, but it is going to have a least square solution. What am I trying to say? there's no solution to this equation, but we can find the solution that is closest to the column space of this matrix. And so we solve this by least squares, or we find the least squares best approximation, and that gives us our M and B, and so that gives us our Y. Now extend this to situations when there's lots of different variables, and you're looking for a linear model between them, or if you want to do something like, say, you want to fit a quadratic model. Instead of doing x1 and 1, we'll expand the variables out to be a full quadratic. So x1 squared, let's say there's two variables. So there's two inputs and one of them that we think is the output based on this. So x2 squared, x1, x2, x1, x2, and 1. And then maybe I should call these y's. Don't judge me, I didn't prepare for this. I'm just doing this on the fly right now. Okay, and then the coefficients of your two variable quadratic would be something like a, b, c, d, 1, 2, 3, 4, 5, 6, e, f. So we think of a polynomial as representing the relationship between our x and y's and our z's. Okay. And we just solved this using linear least squares. Okay. And we know how to do that because we know how to, well, we theoretically know how to do this because we know how to form the normal equation and solve the normal equation. But in practice, it's done in a different way. You can take a numerical linear algebra class and learn about that. You gotta have the background to understand what we'll talk about in there. Okay, so anyway, I'm setting this aside. It's an interesting topic, and you should read it in the book. Read it. Interesting and very important. Basically, anybody in the sciences will encounter, and anybody in statistics will encounter at some point, linear regression. You're trying to fit a model to the data that you have. This is sort of like the most basic possible model. Okay, so we had the least squares problem. We had a normal equation. A transpose AX equals A transpose B. So this becomes we turn a matrix equation without a solution into a related matrix equation that does have a solution, and the solution to this is the closest approximation to the solution to something that gives us what we want, AX equals B. So what we get out of this, I should call this AX hat. So AX hat minus B, the norm of this thing is this. So it's in that sense the best possible solution. And we also talked about A transpose A is symmetric. So the matrix A is called symmetric if A transpose equals A. So this is a matrix that looks like its upper triangle and its lower triangle are like mirror images of each other. It's like you could flip it across the diagonal and the matrix would stay the same. Symmetric matrices are one of the most important classes of matrices in all of linear algebra. And they have a lot of really important properties. And a lot of these properties you might feel, you might have this intuition, are related to diagonalization. Because, well, this is sort of, it's kind of similar to a diagonal. I'm using similar in a non-technical sense right now. It's kind of like a diagonal matrix in the sense that a diagonal matrix is also symmetric. This kind of looks like a diagonal matrix, it's a step on the diagonal that doesn't change when you take the transpose. So let's talk about diagonalization for a second. Ordinarily, we would look for something like this. If we had this, then we call this as diagonalization, where P is some invertible matrix. P is a diagonal matrix. So it only has things on its diagonal, everything else is zero. It only has non-zero matrix on its diagonal. And of course, P has to be invertible because it's inverse. So this is a similarity transformation. And it says that A is similar to D. Now, diagonalization is pretty difficult. It's computationally intensive, right? You remember these problems on the exam taking a long time. What you're essentially doing, well, unless you were given enough information that you could get it right off the bat. Essentially what you're doing is you're figuring out the eigenvalues and the corresponding eigenvectors of A. And that's how you get the diagonalization, right? And that takes a lot of work. It's also the case that maybe the diagonalization doesn't even exist, right? It's possible that the matrix that we're talking about isn't even diagonalizable at all. Okay. So I'm going to introduce a topic that's a slight strengthening. Actually, it's a pretty big strengthening of diagonalization. And that is orthogonal diagonalization. This is the case where P inverse is in fact P transpose, which of course means that P must be orthogonal. And while we're at it, we might as well insist that it's orthonormal. There's no problem in doing that. The columns of P will form a basis for each of the Eigen Spaces. So for each eigenvalue that's on the diagonal of the diagonal matrix, the corresponding columns in P will be the corresponding eigenvectors. And these eigenvectors can be anything so long as they form a basis for the same eigenspace. So we can pick them to be normal. We can pick them to be normal vectors. So why not choose normal vectors, and we have this additional constraint that they're orthogonal columns. Okay. So what must be true of a matrix A in order for it to have an orthogonal diagonalization? Well, if we take a transpose that has this particular orthogonal diagonalization, so this is an orthogonally diagonalizable matrix. It's another form. E transpose transpose. So if it has this diagonalization, then its transpose is equal to this. And remember, the transpose of a product is the product of the transposes, but in reverse order. So this is P transpose transpose, which is just P. D transpose, D is diagonal, so it's just D. D transpose is just D. And then this is D transpose, which is of course A. So, if A is orthogonally diagonalizable, So every orthogonally diagonalizable matrix is symmetric. What about the other direction? Is every symmetric matrix orthogonally diagonalizable? Well, let's, I'll just go straight to the statement of it. So, do this off the cuff or just read it from the book. Yeah, this is a nice statement of it. A is symmetric. And eigenvectors corresponding to different eigenvalues are exponential. That's pretty amazing. Why should this be true? Yes?
Well, I don't understand, if we make something orthogonal, like an orthogonal set, you only need linearly independent vectors.
You can produce, yes, from
So-
any from any linearly independent set, you can produce an orthogonal set. That's a basis for the same space.
Yes, so wouldn't every single diagonalizable matrix have a P that you could make the P orthogonal, right?
You can make the columns of P orthogonal,
Mhm.
right? And there'll be a basis for the same space. Well, of course, P is invertible, so the columns form a basis for all of Rn,
So
whatever spaces.
there's never gonna be a case where a diagonalizable matrix isn't also orthogonally diagonalizable.
Wrong.
Right.
Okay. So let's look at an example. So I'm going to construct a matrix. This is actually fairly straightforward. So maybe let's do this let's not come up with a matrix. Let's actually look at P. So here's an example of P. 1, 0, 1, 1. Okay. Linearly independent, but not orthogonal, right? And I'm going to come up with a diagonal matrix here. 1, 2. And, well, all I have to do is come up with P inverse, and I've gone ahead and constructed a matrix. So we might as well do it. The only thing I've left out is doing the matrix multiplication. So what's the inverse of this? That's easy. It's a 2 by 2 matrix. And then divide by 1 plus 1. So right?
It should be, the determinant should be 0, I think.
Determinant should be 0.
There's 1 minus.
Should be
If the determinant is 0, then this is not invertible.
not 0, just 1, I mean.
1 minus, they didn't hire me for this for my ability to multiply things by 0 and notice that that's equal to 0. I think I added these and then multiplied these. Okay, so that's fine. Anyway, we got our P inverse. So, what happens if I'm going to look at the eigenspaces. There's an eigenspace corresponding to the first eigenvalue, which is 1. So this eigenspace is the span of 0. I actually did that in my head before I came in and I got the right answer. So this is the first eigenspace. Now, the second eigenspace. Lambda 2 is equal to 2. This is the span of 1, 1. Now, if I made these orthogonal to each other, then the two columns together would still span the same space, they would span R2. But this eigenspace, well, we could just leave that one as is and make this one orthogonal to that one. This would now span a different eigenspace. So it would not span the same eigenspace, and therefore it couldn't possibly be the same A. So the different eigenspaces still have the same angles from each other. Does that make sense?
Yeah.
Okay, now let's look at just a little bit different example. In this example, all right, and this covers something that shouldn't be doing this. Using the eraser. Slightly different. We have an eigenspace that's two-dimensional, right, and it corresponds to the eigenvalue 1. And that eigenspace is in fact the whole of R2, right? Now, if I want to orthogonalize these two vectors, I have no problem, because these two vectors are the basis for a single space. And so, although these two vectors are not orthogonal, I can orthogonalize them with the Graham-Schmidt process, for example, and still get a basis for the same space. So in that case, nothing has changed.
Okay.
And that's totally fine. So that's the case in which everything works out, yeah. If there's only one eigenvalue, for example, and the eigenvectors, we have enough eigenvectors to get a basis for the space, right? If this is, we have a single eigenvector, multiplicity 3, for example, we better have 3 independent vectors in the corresponding eigenspace, or otherwise we can't have enough vectors to create an invertible matrix. So in that case, it's totally fine to just take the vectors and orthogonalize them. But what if they come from different eigenspaces? And that's what this says. If A is symmetric, then the eigenvectors from different eigenspaces, the ones corresponding to different eigenvalues, are orthogonal. And that's what I put an exclamation mark after this. That's exciting. So why is this true? Anybody tell me? I'm gonna cheat and look at the book. The book is telling me. So here's why. What we need are V1, V2, eigenvectors from different eigenspaces. This means that their eigenvalues are different, right? So, what is the relationship that these things have? Well, we have that AV1 equals and the 1v1, that's the corresponding eigenvalue. And AV2 equals lambda 2 V2. Right? Now, let's look at the quantity. V1 dot V2. Lambda 1. So lambda 1 times V1 dot V2. This is equal to lambda 1 V1 transpose V2. Considering the course that 1 by 1 matrix we get out, that's a scalar. Okay, so lambda 1 V1 is equal to V1 A transpose. Sorry, V1 transpose A transpose. Make sense? Maybe I should write it like this. A, B1 transpose. And by what we know about how to do take transposes of products, this is B1 transpose, A transpose, B2. But A is symmetric, so A transpose is just A transpose. Take a line break. So that's A, B2, and A, B2. That's a scalar times B2, so I'll pull it out front, and that gives me B1 transpose B2, which is lambda 2 times, what is B1 dot B2. With the mental note in our head that this thing right here we treat as a scalar, this thing right here is actually a matrix that we're just kind of treating as a scalar. So, quotes around the equals. Okay, so if we subtract one side from the other, we get lambda 1 minus lambda 2 times B1 dot B2 is equal to 0. And so, well, I said they were from different Eigen spaces. I should have not spoiled the punchline and said that they just have corresponding eigenvalues, lambda 1 and lambda 2. So when we get to this equation right here, we have two possibilities. Either they come from the same eigenspace, in which they could possibly not be orthogonal, but that's okay, right? As we pointed out before, we can just orthogonalize them, that's fine. Or the dot product is 0 and therefore they're orthogonal. So that write a box to celebrate. We finished the proof. So if A is symmetric, then the eigenvectors corresponding to different eigenvalues are orthogonal. The ones corresponding to the same eigenvalues can be made orthogonal. And so in that case, we can produce, well, a bunch of orthogonal vectors. So what do you think about that? I'm going to write up the book helpfully refers to as the spectral theorem. Symmetric matrices. Just a quick word on this, just a quick explanation of this word spectral. The eigenvalues for a matrix are often called its spectrum. So the set lambda 1 or 2 and k eigenvalues A are sometimes referred to as its spectrum. I think the analogy that you might have in your head is that if you look at I don't know if you're familiar with this idea or not, but if you break down the spectrum or the spectrum of light, so if you're looking at light that's coming off, let's say off of these fluorescent lights right here, when you break down the spectrum, you would see that there's only certain wavelengths of light. So what you're really seeing is a mixture of like particular spikes in the spectrum of the light. And we kind of think of there's an analogy between those spikes and when you break down the light and these eigenvalues. So these are where those things occur. I don't know if that's really where it came from. It turned out that using eigenvalues to analyze light, to analyze data about light, turned out to be connected with actually looking at the spectrum, the actual light spectrum of light, but that was just a coincidence that came afterwards. That was not intentional. Just a nice coincidence. Okay, so an n by n symmetric matrix. N by n symmetric matrix. Following properties. So if it's symmetric, then A has n real eigenvalues counting multiplicity, so no complex no complex eigenvalues. The dimension of the eigenspace I'm going to shorten this one. The dimension of the eigenspaces match their multiplicity, the multiplicity of the corresponding eigenvector. So each of the eigenspaces has enough independent eigenvectors to match the multiplicity of the eigenvalue. The eigenspaces are mutually orthogonal. If you take eigenvectors from different eigenspaces, they're orthogonal to each other. And finally, A is orthogonally diagonalizable. My